All right, so cone revisited. So we got to set this sucker up. Getting the integrals the harder part. So let me draw my cone, and it is totally not to scale, but go with it. So, oh well. Yeah, that's definitely not to scale. So what do I know? I know I have a height from here to here of 11. Oh, my pen is not tracking. Maybe I'll sit down and try the other pen. I don't think I can handle a non-tracking pen today. All right. And radius is 5. So distance from that center over. And we want to pull water out, assuming that this sucker is full of water. And we've been given a rounded weight density here with that happy little music symbol. Okay, whatever that means. It's irrelevant at the moment. So we need to then consider a cross-section of this thing. Choose blue maybe, like this chunk of water right here. And we want to pump it out. Pen, so that chunk needs to come up to the edge and out. Color. So let's see. So it has to traverse some height. So measuring from here down is going to be my height. All right, so what do we know about the radius at this point down here? Well, we know the radius starts off at 5 and it drops down to 0, right?
Yes.
As the height starts off at 0 and drops down to 11. Okay, so then we need a formula based on that information right there. So then the radius is going from 5 to 0, so it has a drop of 5, right? And the height gets to go from 0 to 11, so it has a run of 11. So that's our slope for that situation. And then we need to have our y-intercept for the radius. Where does the radius start again?
0.
Try again.
5.
Starts at 5, right? We're starting pumping water from the top and the level is going to drop. The radius starts out at 5. So that's our formula for the radius as the height goes from 0 up here, and we're going to call the height 11 down there. Okay, so remember I flipped the axis like yesterday? That's my radius formula. How do I find the area of this disk of water there? Pi r squared? Yeah, okay. So then the area in this case is going to be pi times that sucker squared. All right, and that area also has a minuscule thickness, right? So, well, in this case, I'm using h as my variable in that way, so I'm going to call it dh. Oops, I guess I put that in the wrong spot. So I'm going to turn the area into the volume by taking that area and multiplying it by that little thickness dh. All right, so that gives me the volume. I need to then figure out how much that volume weighs. How do I figure that out? What's that? Times the weight density. In this case, they gave me the weight density up here. It's that 10,000 newtons per meter cubed. Yeah, so they're giving me an approximation of the weight density of this liquid. So it's heavy water. So if I want to turn that into force, which is weight, right? Weight. Just force, then I just need to take my weight density, 10,000, and multiply by that chunk of volume. And then I need to do that for all possible chunks of volume, which means add them all up. And our fancy way of adding things is an integral, okay? Now that just gives me the weight. What else do I have to factor in here? Yeah, because I'm trying to find the work, right? And work is weight or force times distance. Okay, so the distance being traveled is h. Yeah, because over here it's 0, over there it's 1, 2, down here it's 11, right? So it's basically our distance is h, that each chunk is traveling. Okay. So so my work then is going to be the integral of my weight times my height. So my weight, is 10,123. My volume is my area times dh, so that's going to be times pi times -5/11 h plus 5 squared, because that's the expression for the radius. I'm going to move the dh out a little bit because I got to squeeze in the distance traveled, which is h, so I can turn this into work. So again, the hard part is setting up the integral, coming up with your formulas. In this case, I'm going to integrate from 0 to 11. So h is going from 0 to 11. And remember, I started measuring 0 at the top and 11 down to the bottom there. So we did the hard part. Next part, let's come up with an answer. To do that, I'm going to have to square that out, multiply it by itself, and then distribute the h through. I like to pull the constants out front. Okay, so why don't all of you try to pull off your own version of that? You can get an antiderivative and then plug it in some kind of calculator to get an amount of work in this case. So give that part a shot next. Pause for a moment and join you. So if I didn't make a mistake, here's my cleaned up integrand and the associated antiderivative. Interesting. All right, I think I have a fractional answer. Let's check it out numerically. And some of these questions ask for exact answers, which means you need to leave pi as pi. What does this one want? Enter an exact value, which means we need to leave pi as pi. Come up with a number for the rest of it. All right, so I'm going to pull pi out of my calculation for now. That right? Oh, what am I messing up? Oh, I did E should stick on X. Okay. All right, so like before I mentioned, it's a good idea to, if you have an antiderivative, type it in as a function into your, whatever your calculating device is. I left pi off, otherwise I'm gonna get an approximation by the tool. And so then I said, hey, what's my antiderivative evaluated at 11? Because when we evaluate at 0, we get 0 in this case, right? Always rethink that. Geogebra says it's, what is this number? 7,562,500 thirds. Okay. I double checked another way. So I don't know if you noticed in my notes here, I was trying to clean up the inside. So I noticed, I'll just highlight what I did here, that there was a 11 squared in the denominator here. And that went into 11 to the 4th power, leaving an 11 squared behind. So the 121 canceled here, that 11 went into the 11 cubed, leaving another 11 squared. Cool thing about that is this term has an 11 squared, this term has an 11 squared, and that term has an 11 squared. So I said, hey, let's just factor the 11 squared out of that whole parentheses. With me? What else is common? Well, there's a 25 here, and there's a 25 living right there, and there's a 25 living right there. So I factored out 25 too. And that left me over here just a 1/4. Over here, it left me with 2/3. And over here, it was just a half. And so then I did a little arithmetic off to the side. 1/4 minus 2/3 plus a half happens to be 1/12. So here's the exact answer in fractional form. And sometimes that works out that way. So I exercise my body, like to exercise my mind with fun with fractions and factoring and arithmetic, in addition to fun with calculus. But cool thing is apparently I did that right because it matches what Geogebra thought my antiderivatives should say. I get the same number each way.
Geogebra does pi. It does exact answer with pi.
Really? So if I put a pi in here, it'll give me pi back?
Uh-huh.
Yep. Oh, look at that! Does Desmos do that too?
No.
Desmos says it's 3.14-ish, and then, okay. Maybe I was thinking of Desmos then, but I was
But
not doing
Geogebra
that.
does pi.
Whoa, it put the pi in a weird spot there. It must be having a graphical glitch because it's in the right spot here. Okay, well, cool, Geogebra. Thank you for that. All right, that was fun and exciting. Is it right? What was the number? 7,500. What was it?
It was 7 million.
7 million, yeah.
7, 5, 6, 2, 5, 0, 0, pi over 3.
Oh, so. You gotta put parentheses.
No, that's okay. Yeah, same thing.
Really?
Yep. Woo, we got it right. All right, let's try this crazy one over here. Okay, so setup. Again, that's the hard part. Integral, that's the easy part. All right, so this one right here, we're going to create a bucket by rotating a curve. And then we're going to fill that bucket with liquid and pump it out. Okay. This particular liquid has a density of 800 kilograms per meter cubed. That is pretty light liquid.
What? What's this?
This is question number 24. Oh, sorry, that's kilograms, not weight density. Oh, so if we take that by now, what's 800 times 9.8?
800 times 9.8.
Yeah. It's like 800 times 10-ish, so that would be what, 8,000?
36.
Okay. What is it?
836.
8,036? So it's a little lighter than water.
800 times
9.8.
9.8.
9.8.
9.8. Yeah, so it's a little lighter than water. All right, so first thing we need to do is graph this thing right here. So this is a log function shifted to the right 2 units. And stretched vertically by 3. So I'm going to guess what this thing looks like. Let's see, normally the log comes through at 1. I'm shifting it over 2, so it should strike the axis at 3. And then it's stretched, so it's going to look something like that. Y equals 3 times natural log of x minus 2. Did anyone graph that to see if I'm making shit up? I think that's accurate.
No, that looks about right.
All right. And then we want to go from 0 to 8. And I have no idea where 8 strikes that. But we can calculate that. So let's see. Do we even need to? What are we rotating about? The y-axis. Okay, so let's see. If I rotate this about the y-axis, I don't even think I need that x value, actually. I would like to use disks here rather than shells. Anybody know why?
Because
Because you don't want to square it?
No.
you don't want to solve that for y.
Oh yeah, I don't want to square it. That's not what I was thinking though. If I went to use disks, then a disk has to be perpendicular to the axis. So this is what a rectangle for a disk would be, right? Just the distance from the y-axis to that curve. That's not too bad. And it's the same from y equals 8 all the way down. If I wanted to use shells, then I would have to make rectangles perpendicular, which means there's y equals 8 up there. Oops, I didn't go high enough. So my rectangle would be from 8 to 0, and then it would be from 8 to this curve. So I need 2 integrals to build that volume. I'm not doing that. Okay? So that's why I would rather use disks than shells here. Get rid of my shells. Okay. Draw this line in again. All right, so we're going to rotate that object. So then I'm going to get this cup that looks something like this. Rotate it about the y-axis. All right, so let's see. When we do that, we are then, so I guess I'll draw in the y-axis through here. There's my y-axis. We're then going to have this chunk of water that we're going to have to pump out. Okay, so this is kind of like the problem we just did, but instead of a cone, I have this funky shape. And I just want to get the liquid over the top edge. So just like before, just over the top edge. So to do that, I need to figure out what that cross-sectional area looks like, which is the result of rotating this thing right here. So I need to know what is that distance right there. Well, that's an x value, right?
Yeah.
Based on this curve. That means I have to solve this curve for x.
You have to add, okay? Was it just one or right?
Nope. No, I just need the distance from the axis to the curve, which is just an x value. The problem is the x value depends on this curve for a given y value. So I have to solve that. So divide by 3. How do we get rid of a logarithm? E. So then I get e to the power y over 3 is equal to x minus 2. Then we add 2, and we get x equals 2 plus e to the power y over 3. And it turns out that right there is the radius, right, of that cross-section. And it's definitely a circular cross-section because I rotated around the y-axis. Okay, so that cross-sectional area right there is pi times r squared. And r here is that x value, that equation. Okay. So then I get pi times e to the y over 3 plus 2 squared is my cross-sectional area. Okay, so then I have to pump, let's see, what else do I need? Oh, I need to turn that into volume. How do I turn that into volume? dy here, yeah. So volume would be that dy. To get the weight, we'll multiply by this, right? We'll do that in a second. Weight is force, right? Then I just need to figure out what's the distance this stuff is traveling. Well, this chunk right here is traveling from whatever that y value is up to, what's that top y value? 8. Okay, how do I find the distance between y and 8? 8 minus y. Yeah. So the distance it's traveling is 8 minus y. All right, so putting all of that together, we now have, switch to red maybe, we now have a work formula. The work is going to be equal to, let's see, we have our weight density, which is 800. Now that's just mass. How do I turn mass into weight? Times 9.8. Right, force due to gravity times the mass gives me the weight. So that times 9.8. Might as well pull the pi out now. Times pi. Those are all my constants. Integrate e to the y over 3 plus 2 squared. That's that. And so the liquid is this region right here. And it's the liquid we need to get out. Yeah, that's the question. Is it from 0 to 5 or 5 to 0? I think it's 5 to 0 because we're pulling the, basically the way you look at this is you're kind of pulling the liquid off the top and it's dropping down as you go. I'm pretty sure it's 5 to 0.
In this case, we'll probably get the same answer.
It would be negative.
Yeah.
No, because of this term right here. The sign, yeah, so if we get the sign backwards, that means we made the wrong decision there.
Okay.
Yeah.
Positive.
Yeah. So, yeah, so if we get a negative number out of this, then we're wrong. Now, here's a complication. I've got to square this. That's not too bad. The complication is when I multiply by y, because what I'm going to end up with in a moment is I'm going to have to take the antiderivative of y e to the something y over 3-ish, something like that. And we don't have a formula for that yet, so we're going to have to use an integral calculator at this point. So why not just plug all of this into the integral calculator right now?
So why didn't you?
Okay,
And we'll
how
do
do-
the harder version of this in 2 weeks.
Okay, so in the integrator, the calculator, do we then do 800 times 9.9 times pi, then times everything that is being integrated?
Yes.
Because you can't put anything to the left of the integrator.
Oh, yeah. So if we wanted to plug this all into the integral calculator, we would have to throw all these constants inside,
And you'd multiply
or
everything
just
by
get
those.
whatever the integral calculator gave us, just multiply by those constants after.
But you would,
Desmos
you'd
can
multiply
do it too.
everything by those.
Desmos can do it too. Yeah, Desmos can do numerical integration.
I think that's most worth
Yeah, it does.
Yeah, we could type that on the outside. Yeah, so let's pull out a tool. Let's see if we can come up with a number and see if we can agree. I think Desmos has been good to me. Geogebra has been good to me today. I'm going to use Geogebra. So I've got 800
Right, that's the
times 9.8.
answer you got earlier, right?
Yeah.
Okay, yeah, it works on that too.
9.8. Ooh, do they want an exact answer here? I don't think this one does. It doesn't say exact. So it turns out we can. It's just kind of complicated. So I'm just going to throw the times pi in there. Times the numerical integral. And then here's my function. So parentheses e raised to the x over 3 plus 2 squared times 8 minus x.
it.
I'm going to use x.
Yeah.
It doesn't matter.
I have to go back.
Yeah, it's a problem if you start switching variables. And I think I was going to start at 5 and end at 0. And, I did it backwards. Yep. I should have gone from 0 to 5.
So do you have to just guess? Or what?
At that direction?
Yeah.
If we
Yeah,
do that
it's
test,
an
we can do
educated guess. All right, so I got, what, 13 million-ish?
That's what I got.
With pi, I got 13 million-ish. If I take pi out, and I don't think I need an exact answer here. I think an approximation will work, but we'll see. Ooh, that's interesting. I got 4 million-ish pi. And the exact answer is going to involve e, if we wanted an exact answer, and pi. So I'm not worried about that. The integral calculator could come up with an exact answer, but I don't know if it's worth it in this case.
Why?
The integral calculator gives you, it's not very pretty.
Yeah.
Yeah, I did it by hand earlier. It took
And
me
it
it took
gives
me over a
you
page.
An approximation in scientific notation.
Yeah.
Why on GeoGebra, when you put in your exact answer, why does it still have the estimated equal sign?
Because GeoGebra, their integration function is not like the integral calculator, where the integral calculator finds a function antiderivative and then evaluates it.
it's still
GeoGebra is doing
estimated.
something like Riemann sums
So it's still
with a
gonna be
million
estimated.
rectangles. So it's just a guess, and
So
it's
can-
accurate to a lot of decimal places.
So
so-
you can't really get an exact.
You can't get an exact answer with integration out of GeoGebra.
Okay,
You cannot. The integral calculator will try. So I think I got that right.
but my open math will still take the one from GeoGebra, or do we have to put it? In
This
the
particular problem didn't need an exact answer with pi.
Or I mean,
I'm
if it was
90%
an exact
sure.
one. That's the other one. It does take the.
Yeah, so here, blow that up just a little bit. It would take an exact answer if you had one. Yeah, so here's the antiderivative, one version of the antiderivative right there. So an exact answer is going to involve e as the base, right, in multiple spots. And we will actually, in about 2 weeks, learn how to come up with that based on the initial function. Yeah, that's chapter 3. That's the real fun stuff. Okay, So we have an answer. Somebody want to tell me what the answer was? It was 12 million. I'm going to go without the pi. Does anybody have the 12 million-ish answer? 13 million. What was it? 13 million? That's more decimals or numbers.
Oh,
More
one,
than just
five,
What is it? 1,
5,
5, 6.
5, 7.
Three.
3.
125.
Okay, I don't think the point's going to matter, but submit. Woo, got it right. Yeah, 13 million. Who cares about a quarter, right? Okay. So the magnet problem actually isn't very hard. The interesting thing about the magnetic force is kind of similar to gravitational force. The further you move away from the object, the weaker the force is. And a lot of those things, light, gravity, magnetic fields, work on what's called the inverse square law. So the force is proportional, K, to the reciprocal of the square of the distance they are apart. That's what this formula says. And again, that's how gravity works. That's how light diffusion works. That's how magnetic fields work, which is pretty cool. So they give me the force equation, right? And how do we calculate work? Force times distance, right? And the distance in this case is just a whole bunch of dx's added up, right? Integral adds up little chunks of x. Okay, so we take the force at each distance and add them up. So in this case, the formula is actually pretty straightforward. It's just your force equation integrated. That's it. So let's set that up, and then I want to talk about centers of mass. Oops, wrong screen. Okay, now, problem is you don't always have the force constant, so you have to calculate that sometimes. So they gave me some information to try and calculate it. So they're saying, suppose when the two magnets are 0.05 meters apart, so about 5 centimeters apart, the force between them is about 2 newtons. So you're trying, so let's say they're opposites, or they're the same polarization, you're trying to push them together. And so if we took a force meter, at that moment they were 5 centimeters apart, it would measure 2 newtons. Okay. So we can feel that magnetic field pushing these magnets apart, and we feel that force at that point. So calculating from there, we're given the force of 2 newtons. So in terms of force equals K over d squared, we have the force is 2. That has to be K over the distance squared. Distance is 0.05 squared. And remember, newtons is a measurement of kilogram meter per second squared is what a newton is. And so that this measurement is newtons means it's compatible, right? And we usually have to think a little bit about compatible units. So then K, solving here, must just be 2 times whatever 0.05 squared is. I'm just going to leave it that way rather than multiply it out. And we want to find the work that's required to move the magnets from a distance of 0.03 meters apart to 0.09. Okay, so I guess maybe they must be pulling each other together then, because we're trying to pull them apart here. So then we just want to integrate this thing from x equals 0.3 to 0.09, oops, 0.03, sorry about that. So 3 centimeters to 9 centimeters, but measured in meters. And our force function is K is 2 times 0.05 squared divided by our distance we're going to call x squared. So that's our force function. And integrating the force function with respect to x is going to give us our work. Yeah, so magnets, once we have this formula and we know the constant, it's a relatively simple application of calculating work from force. So I'm very confident you guys can finish that off because we have an integral set up. So yours will be pretty similar. Your numbers will be slightly different in terms of where they start and where they end. And because we have newtons times meters, the answer is definitely going to be in joules, right? Because we're measuring in meters and we have a force in newtons. Okay, cool. Next exciting topic. Hold on to yourselves. Oh, we're almost out of time. Darn.
Can you do it in?
We're officially a day behind today. That's okay. So that means the test will not be what I'm projecting. Unless we catch up. All right, so next topic. What is this, 2.6? Is that really what we're on now?
Yeah.
Oh my gosh. Okay. So 2.6, centers of mass and moments. So idea of center of mass, we'll start off in one dimension, then we'll work our way up to two dimensions in a couple of ways. So one dimensionally, if you think about it, if you have some weight over here, maybe that weight is 4, and you have some other weight over here, maybe that weight is 1 unit. Where would we put a balance point so that this stayed even, balanced?
Closer to
Okay.
4.
Yeah, it's going to be closer to 4, right? Because we need more lever outside there to kind of balance it out. Okay. So turns out centers of mass are just weighted averages. No joke there. Okay. And so I'll give you an example and show you that weighted average. And then we'll try it in 2 dimensions, and then we're not going to have time for the calculus version today, unfortunately. We'll do that next time. So let's suppose we have, I'm going to use a number line. Here's 0, 1 over there, and 1, -2 over there. And I'm going to put a mass over here that is 7, say, kilograms. And then I'm going to put a mass over here, and that one's only going to be 5 kilograms. So the mass is centered on 2, and the mass is centered on -2. So then the question is, well, where then would I find the balance point of this system, right? And basically, it just goes like this. You just consider the position of that 5 right there. Well, it's at a position of -2, and that -2 has a weight of 5. Okay, so I have position times weight. And I have another weight that has a position of 2, and its weight is 7. Okay. Now, if you think about the idea of average, average means add it up and divide by how much stuff there was. Yeah, and how much stuff there is the total mass. So the total mass here is just 5 plus 7. So that's the idea of a weighted average. The positions are weighted by what? Well, actual weights in this case, right? GPA works that also. Like, is getting an A in the 4-credit class, is that the same as getting an A in a 2-credit class?
No.
No, you got more, work you did for that A in the 4-credit class, so it should be worth more, right? So same idea applies to GPAs and a whole bunch of other things in life. So there's my weighted average right there. So cleaning that up, what do we get? 10 plus 14, that's 4.
-10 plus 14 should be 4.
-10 plus 14, that's what I meant, yeah. Which is 4, and then 5 plus 7 is 12, and 4 divided by 12 is 1/3. So that means if we locate 1/3 here on the number line, so that's 1/3 would be about right there-ish. That would be the center of mass for this system right here. Okay. And the idea of a moment, this number up at the top right there, that's called the moment here. The weight, the total weight, based on position. And so if we were to put these things on a ruler and we were to put our finger at the point 1/3, we would have this thing in equilibrium. It would just sit in balance on top of our finger. And it would be kind of like all of the weight was sitting on top of our finger. Okay? And the moment kind of represents all of the weight. Bring it over there. So it's the place that keeps the system in equilibrium. So that's the idea of a moment in one dimension. Now let's go to 2 dimensions. 2D moments. All right, so let's say I have mass number 1 of 2 kilograms, and it's at 0.1, which is the 0.32. I have mass number 2, and I'm going to double the weight to 4, and it's going to be at 0.2, which is going to be -44. And we have mass number 3. I'm going to double the weight again, make that 8. It's going to be at 0.3, which I'm going to call -52. And let's do mass 4 for fun. And it's going to double again, 16 kilograms. And I'm going to put that at 0.4, which is going to be 1, -6. All right, rough sketch of that scenario. Let's see, 1, 2, 3, 1, 2. So I have a mass right there of 2, right? So I'm just going to put a little dot there. And then go this way, 1, 2, 3, -4, up 4. I've got a mass over here that is twice as big, so I'm just going to make it a slightly bigger dot. -4, 4, and then where am I? -5. That should be a -2 there, sorry. -5, -2. I wanted to jump into the 3rd quadrant. So let's see, -5, -2, that's about here. And that one's going to be twice as big as the 4 dot. So maybe it's what, like that big-ish? This is 2, this is 4, that's 8. And then where am I next? At 1, -6. So 3, 4, 5, down here-ish is -6. And so right around here, I have a mass that's even bigger than the last one. Okay. So each of these is centered and has a mass going from 2 to 4 to 8 to 16 there. So the question is, imagine this is some plate, okay? And the plate is centered on the origin. If I put my finger on the origin, this plate is going to tilt because the origin is not the center of mass at those points. So the question is, where is the center of mass? Well, it turns out it's just a weighted average for x and y. So if I wanted to find the center of mass here, I would just take the x values times their weight and add them all up. So I just do the one-dimensional version in each direction, right? So the center x value, I'm going to call that x bar, is just going to be 3 times its weight of 2 plus -4 times its weight of 4 plus -5 times its weight of 8 plus 1 times its weight of 16. And all of that gets divided by the total mass, which would be 16 plus 8 plus 4. Does that add up to 20, 30? No, wait, 40?
Plus
10,
30.
30. I was right the first time. Yeah. So that's the weighted average y bar, oops, average y value in this case for this would just be do the same thing with the y's. So take the position of y 2 times its weight of 2 plus the position 4 times its weight of 4 plus the position -2 for y times its weight of 8 plus the position -6 times its weight of 16. That weights the masses with y, then divide by the total mass. So we just took the 1D thing, made it 2D. All right, and I forgot to write down my answer, darn it. According to my printout, I got the answer something like -1,3-ish, approximately -1, -3, sorry.
Yeah, that's me.
So -1, -3. -1, 3. So somewhere over here. My recollection is it was a little more than, it was like -1 1/3 maybe, and -3.1-ish. So somewhere over here, that's my center of mass. When we're in a plate like that, we call that center of mass a centroid, two-dimensional center. Okay. Now, what if we had, instead of these point masses, I know we're out of time. What if we had like a whole bunch of sand covering this, more like a continuous, and the sand is like piled up in funky spots? Well, then we would have to add up a ton of grains of sand, which is what an integral does.
Oh my god.
So these sums in the numerator are just going to turn to integrals. So that's what we're going to do next on Friday, tomorrow?
Yes.
Tomorrow, yeah. So I will shift the due dates of these next few assignments all a day each. Give you guys a little more breathing room. Yeah, so you have enough information to do problems 1 and 2 of that next homework, if you would like. We got a bit more work to do for the others.